45. All right. Here, don't make this go around. Make sure everybody signs it. Everybody except her. Don't anybody let her sign nothing. Okay, 45 and 25, right? An object starts from rest and falls under the influence of gravity. Draw graphs of A, its speed, and B, the distance it has fallen, as a function of time from t equals 0 to t equals 5 seconds. Morning, Tyler. Let's see. All right. Object falls under gravity. So we've got y equals y sub naught plus v sub naught t minus 1/2 gt squared. Did I get that right? I did. We've got to pick a point at which it starts falling. Since we don't know how high it is, we just know how far it's going to fall. So let's pick wherever it starts at as y equals 0. And then we'll calculate how far it falls as a function of time. So y as a function of time is equal to 0. And we know it starts from rest, so that's 0 minus 1/2 gt squared. And 1/2 of 9.8 meters per second squared is 4.9. Is that right? Okay. Taking your words for it. Now we want to plot this from 0 to what, 5 seconds is it? Yeah. So let's draw our graph. See what I did? I labeled the y-axis going up to a negative y. That way we don't have to draw the graph upside down. Here we've got 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. All right, now it's just a matter of plugging in values. What's 1? Keep 1 squared. 1 squared is 1, so at y at t equals 1, y will be minus .9 meters. 2 squared is 4. What's 4 times minus? Two squared is 4. 4 times minus 4.9 is, say again, minus 19.6 meters. 3 squared is 9. 9 times 4.9. minus 44.1. 4 squared is 16 times 4.9. 78 point what? 0.4. Okay, and who asked this question? Saul? Okay, break out your calculator. You're not going to let her do all your work, right? Okay, 5 squared is 25 times 4.9. Yep, 4.9 times 25 times 5 squared. 122.5. So we're going to go from 0 meters to 122.5 meters. Let's see. How are we going to divide this up? 125 is 62 and a half, so we'll call it. There we go. Now we've got our scales. At 1 second, we are at minus 4.9. At 2 seconds, we are at minus 19.6. At 3 seconds, we're at minus 44. At 4 seconds, we're at minus 78.4. And at 5 seconds, we're at minus 122 and change. And there's your graph. Now that's its position as a function of time. How would we find its velocity as a function of time? Its speed. I think the first one would be the simplest, right? We start at 0, and the acceleration is minus 9.8. So now we're going to write v equals 0 minus 9.8 meters per second squared times seconds, right? So at 1 second, its velocity is here, let me clean this up. We're using v equals v sub naught plus a t, which in this case is 0 minus 9.8 meters per second squared times time. So at 1 second, what is minus 9.8 meters per second squared times 1 second? Minus 9.8. at 2 seconds, it's 9.8 times 2. Minus 19.6. Now, 9.8 times 3. 29.4, you said? Okay. 4 seconds. 5 seconds. All right. Sorry about this, Shy, but I'm going to have to switch colors on you. Now for velocity, at 1 second, we're at 9.8. Right there. At 2 seconds, we're at 19.6. Right there. At 3, we're at 29.4. And at 4, we're at 39. And at 5, we're at minus 49. There's your velocity as a function of time. What do you notice immediately about these two graphs? They're both increasing. What is the relative shapes? Ignoring the added squiggle that I put in by drawing it freehand. This one is parabolic. It's nonlinear. Position is nonlinear. It's parabolic. It goes as t squared. Morning, Alexia. Velocity is linear. It goes as t to the power of 1. All right. That's 45. 45, right? Yeah. Now, who asked? Someone asked for 25? You asked for 25? Got your pictures? All right. 25. Baseball pitcher throws a baseball with a speed of 43 meters per second. Estimate the average acceleration of the ball during the throwing motion. In throwing the baseball, the pitcher accelerates it through a displacement of about 3.5 meters from behind the body to the point where it is released. Okay? What are we going to look for? What are we going to solve for? Average acceleration. Okay, which of these equations do we want to use? What information do we have? Let's go think back to the problem solving. We have the final velocity, and we have the total distance, but we don't have time. We need acceleration. I'm liking that one, right? It uses the only thing, everything in it is what we either want to know or already know. So let's use that one. V squared, pay attention, Shay. V squared equals V naught squared plus 2a delta x. Am I getting that right? Okay. Delta x is, oh, did she leave? We didn't need to know that, but thank you. 2a. The distance, delta x, is 3.5 meters. V naught is 0 because when he's starting to throw, it's at rest, it's not moving. And its final velocity is, what did it say, 43 meters per second. So we've got 43 meters per second squared equals 0 plus 2a times 3.5 meters. What's 43 squared? $1,849 equals 2 times a times 3.5 meters. That would be 1849 meters squared per second squared. So if we divide that by 3.5 meters, what's 1849 divided by 3.5 meters? Equals what? Meters squared per second squared divided by meters leaves meters per second squared. And that's equal to 2 times a. So divide that last number you got by 2, and what do we get? Meters per second squared equals a. We got the right units that we wanted, meters per second squared. All we need to do now is make sure we're only using the appropriate number of significant digits. 2 significant digits, 2 significant digits. What is this answer to 2 significant digits? 260 meters per second squared. And that is our final answer. Didn't even have to phone a friend. Although I guess I did use ask the audience, right? Okay, well, that's 2 free homework problems. Now, before we continue with class, I want to make sure everybody remembers we have a holiday on Monday. That's definitely going to interfere with our exam on Monday. We do have an exam coming up next week. We'll just have to do it on Wednesday. And I think I'm probably going to make it a take-home exam because I don't want it to mess with my schedule. So that probably means y'all will score much better on this one. Or if you don't, it's your fault. Say again? Okay. Well, no, everybody has to come in on Monday to give me the homework. No, we don't have, we're not going to be here, so it's not due until Wednesday too. That's correct. I'm sorry, I shouldn't be that sarcastic. All right. Homework is due on Wednesday too. Now, last time we were looking at, I hope everybody still has all your kinematic equations in your notes. As you have begun to notice, we need them frequently. Now, this is where I left y'all. Who, besides Shay, has seen the problem, has found the error? You have? Wait, don't say it out loud yet. Who else has spotted the problem? How did we spot the problem? You think you got it? Right? What's the very first thing we noticed? When we divided these numbers, we ended up with a total distance of 0.77, I think it was, 3/4 of a... Actually, if you analyze the unit, well, first of all, 0.77 doesn't make any sense. Expecting a distance, if you throw a ball with 15 meters per second of velocity, it's going to go a lot further than just that far before it stops. Okay, so that's the first, that should have been the first indication that, wait a minute, something ain't right here. The very next thing we should see is, what do we end up with when we divide meters per second by meters per second squared? We end up with seconds. So we're saying that y meters is equal to 3/4 of a second? That just doesn't make sense. That sounds stupid even when I say it. So, where's the problem? Galde, what do you think the first mistake was? Does everyone see what he's talking about? This was this is our equation. We start with v squared. We're solving for the point when v, the velocity, equals 0. So we start there with 0 squared. That's supposed to be equal to v naught squared, not just v naught. Right? Now, let's take another crack at this problem and see if we get it right. We're still looking for the point when v is 0, so 0 meters per second squared equals the initial velocity, 15 meters per second, squared, minus 2 times g times y minus y naught equals 0. Okay? This is a g. So we've got, what is 15 squared now? Say again? 225 minus 225 meters squared per second squared is equal to minus 2 times 9.8 meters per second squared times y meters, which would give us meters squared per second squared, meters squared per second squared. What's 2 times 9.8? That's 19.6. Now we have the negatives canceling out. Meters squared per second squared divided by 19.6 meters per second squared equals y meters. Second squared per second squared cancel. One of the meters cancels. We're left with meters equal meters. So it looks better already. Now what's the arithmetic say? 225 divided by 19.6 11.4 meters. That's about 30 feet, 35 feet, something like that. That seems a whole lot more reasonable than 3/4 of a meter. I also want to point out to you that even though we're dealing with a negative acceleration, we still ended up with a positive displacement because of our initial velocity. Okay. Anybody have any questions about this one? What else do I need to? I want to make sure. Yeah, I don't really care for it, but I want to make sure we cover section 2.2-8 at least well enough for you to do the homework. This is a pretty good little problem for using these kinematic equations. Let's look at it. Let's take another approach to this one. If you go to page 36, look at example 213. In this one, we're going to look at how long the ball is in the air before it comes back to the hand. In other words, how long does it take the ball to reach the top and then come back down? And before we do that, I'm going to ask y'all to put on your thinking caps. Make a guess. Who thinks it'll reach the apex at the midpoint of its flight? In other words, that it'll take as much time for it to go from here to here as it will for it to go from here back to here. Or will one leg of the trip take longer than the other? Think it'll take longer going up than it does coming back down? Okay. I don't know. Hardest part of being right all the time is learning that I don't know is usually the right answer. Who else has a guess? Look at the kinematic equation. Which one are we going to use? This time we're going to be looking for time. We have all of the other components, all the other elements of that equation. The one variable we don't know is time, and that's the one we're going to be solving for. So this is one we're going to be using. All right, well, let's solve it and see. We know that y is equal to y sub naught plus v sub naught times t minus 4.9 meters per second squared. Is everybody okay with me going ahead and dividing 9.8 by 2? Taking the 1/2 g and doing that already. Times t squared. That's where the 4.9 comes from. It's minus 9.8 divided by 2. Half the acceleration. And y sub naught is 0. The initial velocity is 15 meters per second times t minus 4.9 meters per second squared times t squared. Now what do we do? what would you do next? Say again. How many of you would break out the quadratic equation? Because I got to tell you, the truth is, that would be a perfectly acceptable way to find the solution. We're looking for y, the final y equals 0. So we could set that y equal to 0 and then solve it using the quadratic equation to determine when, how long t. And we would get, you're familiar with the quadratic equation, we would get two values of t, right? But in this case, there's a simpler way to do it. What if we factor out 1t here? We get y equals t times 15 meters per second minus 4.9 meters per second squared times t. All right? Nope. We factored out 1t from here and 1t from there. So we've got two factors. We've got t and this t. And we're looking for when y is going to be equal to 0. And that's crucial here. That's important. In order for this product to be equal to 0, what must be true? No. One of the two factors must equal 0. Anything times 0 is equal to 0. And nothing times anything other than 0 will ever be equal to 0. Does everyone understand that? If you have two non-zero numbers, you can never multiply them together to make 0. You can make a negative number or a positive number, but the only way you can get 0 is if you multiply something by 0. That means either t has to be 0, which is a trivial solution. It was at y equals 0 when t was equal to 0, before you let go of the ball. It will be back at y equals 0 when this is equal to 0. So we solve that for 0 as times t. So, am I blocking too many people's view? Minus 15 meters per second is equal to minus 4.9 meters per second squared times t. Divide both sides by minus 4.9. The negatives cancel out. We get 15 divided by 4.9 meters per second divided by meters per second squared gives us seconds equals t. What's 15 divided by 4.9? It's going to be just a hair over 3. 3.1. So, the ball will be at y equals 0, at t equals 0, and at t equals 3.1 seconds. Yeah, you should have kept 3 significant digits. 3.06, right. So now how do we figure out which which leg of the trip took longer? Say again. We already know that this height is 11.4 meters. Right? We know that the starting position is 0, that the velocity will be 0 at the top. So the only thing we're looking for now is how long will it take the ball to go from 0 to 11.4 meters at minus 4.9 meters per second squared. Everyone see what I'm doing? We're starting off with y equals y naught plus v naught t minus, am I doing that right? Yeah. Minus 4.9 meters per second squared times t squared. Well, v naught is 15 meters per second. I misspoke a moment ago. Y naught is 0. So that's going to equal 15 meters per second times t minus 4.9 meters per second squared times t squared will equal 11.4 meters. Now, how do we solve that? Now we need the quadratic formula. We subtract that from both sides. We write this in the form of the standard form of a quadratic equation. We subtract the constant from both sides. Put the squared term first, minus 4.9 meters per second squared times t squared plus 15 meters per second times t minus 11.4 meters. 4.9 meters per second squared times second squared leaves meters. Meters per second times second leaves meters, so the units all match up. A, B, and C. A, B, and C. And we fill in. So we're looking for minus 15 minus B plus or minus the square root of 15 squared minus 4 times 4.9 negative times negative 11.4 minus 4AC. All of that divided by minus 9.8. 2A, 2 times A. What's this product? Oh. Well, wait, first of all, what's 15 squared, somebody? 225? Now, 4 times 4.9 times 11.4. Say again. 223.44. And that's a negative times a negative is a positive, so it's minus that. What's the difference here? Say again. All right, minus 15 plus or minus the square root of 1.56 divided by minus 9.8. And what's 1.56? What's the square root of that? 1.24. All right, so we've got minus 15 plus 1.24 divided by minus 9.8. And we've got minus 15 minus 1.24 divided by minus 9.8. What are those? Say again. Oh, negative. Which one's equal? What are you? This negative 15 plus buddy. That's the whole thing. 1.4. And the bottom one, the whole thing is 0.11. What are those? Negative. Let me see a calculator. Somebody else do this bottom one. All right. 1.6. Actually 1.66. And that gives us, what's the sum of those two? 3.06. That's the total time. So the point is that we found out that the two branches are not the same time, that it doesn't reach the midpoint, the apex, at the middle of the time. The total time it spends in the air is not equally divided between the two branches. Right? Say again? No, it's because of in fact, we ignored air resistance altogether. That's because of the fact that on the way up, it has an initial velocity pushing it that way, and the acceleration is pushing it down. But from the top, it starts off with an initial velocity of 0 and is only accelerated in the opposite direction. So it comes down the second side faster than it takes longer to get to the top than it did to get down. Any questions? Any questions about the homework or anything at all from Chapter 2? Because the exam is going to cover all of Chapter 2. All right, well, let's talk real quick about this graphical analysis of linear motion. We looked at that homework problem right out of the gate. Where we plotted position as a function of time and velocity as a function of time. Okay, let's look at a couple of these. That graph is position as a function of time. If we look at it from here to here, what do you notice about it in that region, in that domain of the graph? That it is linear, which means what? What is it called when position is changing in time? Velocity. If position is changing in time, and that change is happening linearly, what does that tell you? That the velocity is constant. Okay? From here to here, the position as a function of time, again, is linear. And in this case, in fact, it's not just linear, it's constant. What does that tell you? That the velocity is not only constant, but it's constant at zero. The velocity is constant at zero. Because the position is not changing during that period of time. Again, from here to here, you've got the position is changing linearly, which means in that domain, the velocity is constant. The change in position is linear. If we were plotting velocity as a function of time, from here to here, that velocity would be some constant value. What would we know about the velocity from here to here? We would know that the velocity is constant and that it's zero. Because from there to there, position isn't changing at all. Did I go too far with that? Yeah, a little bit. Then from here to here, what do we know about the velocity? That it's constant and negative and changing a lot more than it was here. Because this is a much steeper, so it's changing in the negative direction, but it's also changing more per unit time. So from here to here, it would be way down here. Everyone understand this? Looking just at this position, this part of the graph from here to here. The change in position from here to here is delta x. I'm sorry, I did that backwards. That's not delta x, that's delta t. This is delta x. So the slope of this line is equal to delta x divided by delta t. That's, I used m. I don't want to use m because that's using m from the equation of a line mx plus b. But the slope of that line is actually delta x divided by delta t, which is velocity. Now, if you were taking calculus, then you could find the slope of this line even here where it's curved by taking the derivative of the function and position as a function of time. We're not going into calculus. So we're going to stick to strictly the linear parts of the graph. But if we were doing the calculus, we were looking at x as a function of t, some curved function, then the derivative of that function at any point would be the velocity at that point in time. You'll notice here it's positive, so it would be there. Here it's still positive, but not as much. Here it's even more positive, and here it's come down a little bit. So if we were plotting the velocity as a function of time, we'd have something that looked like that. If this graph of position as a function of time actually turned and went negative, then there you would see the velocity function go negative. If you in turn then began to apply the same kind of taking the derivative to find the slope of the velocity as a function of time, what would that tell you? What's it called when you change velocity in time? That would be acceleration. If instead of plotting x as a function of time, we plotted v as a function of time, then the slope of that function would be our acceleration at that point, at any point in time. Okay? I think the easiest way to do this would be to just talk about the homework problem. The only one you have that's going to involve this, number 55. Turn to page 45 and look at problem number 55. It shows the velocity of a train as a function of time. At what point, at what time is its velocity the greatest? I didn't? Seriously? 55 is not in the homework assignment? Well, never mind. I guess I did remember to go back and take it out. In that case, have a good holiday weekend.